Your spacecraft is in clean sunlight, and the flight computer suddenly thinks it's tumbling. Star trackers disagree. The attitude system starts correcting a motion that isn't real. Power currents twitch like someone bumped a breaker. If you're watching telemetry, you recognize the feeling. The sun just reached into your mission from 93 million miles away. No mechanic, no spare parts, no guarantee a restart brings you back the same. You choose what stays powered, what goes quiet, and whether the spacecraft fights through it or drops into survival mode. So what's your move? If you're in the middle of a critical pass and the storm warning hits, do you keep collecting data? Or do you safe the spacecraft and protect the bus? Drop it in the comments, because solar storm protection isn't one magic trick. It's a design story across decades and across very different spacecraft. Early, low-power satellites, geostationary communications workhorses, deep space probes that can't get real-time help, delicate observatories, armored flagships, and modern constellations that survive by distribution. What a solar storm really does to a spacecraft. A solar storm doesn't arrive as one clean problem. It arrives as stacked problems that look like confusion. Particles can punch through electronics in flip bits. One flip bit might be nothing, or it might become a fake sensor reading, a bogus fault flag, or a bad command. Charging can build up on surfaces and inside materials, then discharge like a tiny lightning strike. And for low Earth orbit spacecraft, geomagnetic activity can heat the upper atmosphere so it expands upward. Density rises at altitude, drag rises with it, and the spacecraft starts losing energy faster than planned. Those effects pile on at once, so the real goal isn't beat the sun. The goal is stay stable long enough to recover. The warning game, why you sometimes get only minutes. Operators live on lead time. Upstream monitors sample the solar wind before it hits Earth's neighborhood. Sometimes that buys close to an hour. Sometimes it's a lot less. That uncertainty changed design philosophy. Human-made protection sequences still matter, but modern spacecraft lean hard on onboard fault rules, fixed thresholds, watchdog timers, and automatic safe hold behavior that triggers faster than a debate. The first generation, simple survival before smart survival. In the late 1950s and early 1960s, satellites survived by being simple, not by being smart. Explorer 1, launched in 1958, ran on chemical batteries that died after a few months and used early transistor electronics. Protection was simplicity itself, conservative limits and short lifespans. Then the early 1960s boom hits. Weather satellites like Tyros, navigation experiments like Transit, and communications breakthroughs like Telstar and SYNCOM. These spacecraft were proving the concept of space as infrastructure, but the hardware was still fragile by modern standards. Telstar 1 launched in 1962 with thousands of solar cells, nickel-cadmium batteries, and a much larger transistor count than the earliest satellites. It proved global relay was possible, and then radiation damage accumulated until key electronics failed. That era shows you what early space hardware lacked, especially from 1958 through the mid-1960s. Often single-string command chains, limited sensor cross-checking, thin fault logic, modest shielding because mass was precious, and very little onboard self-rescue if a sensor started lying. It also meant real physical vulnerabilities. Early power systems had less margin, so a storm-driven attitude error that reduced sun exposure could drain batteries quickly. Thermal control was simpler too, so an unexpected pointing change could swing temperatures in ways that stressed components. And memory and computing were limited, so there was less room for robust error detection and correction. Stabilization choices reveal the mindset. Many early spacecraft leaned on spin stabilization or simple sun sensors because precise three-axis pointing was harder to do reliably with the sensors and computing available. Fewer sensors meant fewer disagreements. until the one sensor you trusted got noisy. Over time, spacecraft kept that simplicity as a fallback mode, but added the missing layer, a self-rescue playbook. Safe mode, the most important spacecraft move you never see. Safe mode is the universal survival posture. The intent is consistent. Stop performing, start surviving. In safe mode, instruments shut down. High-voltage systems go quiet. Attitude control simplifies to the most reliable sensors available. Power and thermal stability come first. Communications falls back to the most dependable link, so the ground can still reach the spacecraft. And safe mode has a real price tag. During the intense October 2003 storm period, NASA's Mars Odyssey entered safe mode during severe radiation conditions. Its MARIE radiation instrument tripped a temperature alarm, was powered off, and was not expected to recover. In that same storm window, Japan's Kodama data relay satellite also went into safe mode. When a relay satellite safes, it can't relay like normal. That's what cost looks like. You lose instrument time right when the environment is most interesting. You can miss a scheduled downlink pass. You can blow a maneuver window you planned for weeks. Even outside storms, safe mode shows how unforgiving timing can be. Cassini experienced a safing event that interrupted the downlink of close flyby data at Iapetus. Nobody lost the spacecraft, but the mission lost time, lost schedule margin, and had to claw its way back into the planned timeline. Solar storms just add insult to that reality. Safe mode is often the right call, and it still hurts. Geostationary workhorses, how charging mitigation actually works. Geostationary communications satellites are built to run for years with boring reliability. They're also vulnerable to charging during disturbed space weather. The dangerous moment is discharge, a snap that can inject a spike into electronics or create a glitch in the control chain. So mitigation became concrete engineering. Modern designs try to keep exterior surfaces from becoming isolated charge pockets. Thermal hardware like optical solar reflectors and blanket layers can use grounded, transparent, conductive coatings, such as indium tin oxide, so charge bleeds away instead of building up. Multi-layer insulation often uses Kapton-based blanket materials, but the important part is how those layers are bonded and grounded so you don't accidentally create little, isolated conductors that charge up on their own. Grounding and bonding do the rest. Bond straps tie panels and structures to a common electrical reference. Designers avoid leaving floating conductive islands in blankets. Harness routing and shielding reduce how much a discharge couples into sensitive lines. And transient protection helps keep an electrostatic event from turning into a reset or a bad command. There's also an operations equals design piece here. Many geostationary teams treat storm windows like severe weather at an airport. You don't do the fancy stuff. You hold your posture, keep margins healthy, and wait for the environment to calm down. Deep space probes, how you prevent a cascade when Earth is minutes away. Deep space missions don't get real-time help. Distance turns operator reflex into operator patience. Out there, the enemy is cascade, a small upset turning into a control problem, then a power problem. Error-correcting memory is one of the main breaks on that slide. Extra check bits are stored with the data. If a single bit flips, the system can detect and correct it automatically. If the error is too large, it gets flagged and forces a safe response. Reset a processor, switch to a redundant path, or reboot into a known good configuration. Mars Odyssey gives a storm time example. During the October 2003 event window, the spacecraft experienced a memory error during a downlink session, and the issue was corrected with a cold reboot. That's cascade prevention in plain form. Stop trusting questionable memory before corrupted data can steer the spacecraft. Now make that idea more tangible. If a bit flips inside a stored star tracker solution, you could think you're pointed somewhere you're not. If a bit flips inside a thruster table, You could fire the right thruster for the wrong duration. Error correction and watchdog logic exist so the spacecraft doesn't keep confidently driving with a broken speedometer. Deep space fault protection also cross-checks sensors. If Star Tracker output starts contradicting sun sensors and gyros, the spacecraft can downshift into a simpler pointing mode instead of letting one noisy input drive the bus. And deep space craft usually carry redundancy not just in parts, but in pathways. Multiple computers, multiple sensor strings, and safe hold modes that can run on the minimum viable brain while the rest gets reset. The armored approach: vaults, spot shielding, and protect the brain. Some missions don't just harden parts, they build armor. This is the vault mentality. Protect what absolutely must survive. Juno carries a dedicated radiation vault with titanium walls about 1 centimeter thick. Inside are the electronic boxes that keep the spacecraft thinking: command and data handling, power control, and other critical assemblies. Europa Clipper uses the same logic in an aluminum vault about 1 centimeter thick to house sensitive electronics. Instead of shielding every box separately, you create a protected neighborhood and put the most vulnerable hardware inside it. Then there's spot shielding. Dense materials such as tantalum can be used in targeted enclosures where a few extra millimeters make a big difference. Some subsystems even use mini-vault approaches, thick structure plus dense, hot spot shielding, because the environment won't treat every location equally. The armored approach also changes what parts you choose. For high radiation missions, designers lean on radiation-hardened processors, conservative clock speeds, and simpler, more predictable software behavior. You trade raw performance for survival, and it changes layout. The brain gets tucked deeper in the spacecraft, sometimes behind propellant tanks or other mass, because every layer helps. Critical harness runs get routed with more paranoia. The command chain is treated like a life support system for the spacecraft itself. Delicate observatories, when your payload is a giant eye. Observatories can be robust buses carrying extremely sensitive instruments. Particle events can spike detector noise. Charging can stress high-voltage subsystems. And even small pointing trouble can create calibration work that drags on. So they protect themselves with a strict hierarchy. Keep attitude stable, keep thermal stable, then bring instruments back carefully. Missing data hurts. Losing alignment hurts more. Constellations and small spacecraft: why drag spikes can kill new satellites. Modern space isn't always one flagship. Sometimes it's a fleet. Small satellites often can't carry heavy shielding everywhere, so resilience shifts toward fast recovery. Reboot cleanly, restore attitude, rejoin the network. But storms hit fleets in a second way: the atmosphere. A geomagnetic storm heats the upper atmosphere. The thermosphere expands, increasing density at the altitudes where low Earth orbit satellites fly. Density rises, drag rises, and the satellites lose energy faster. If they drop, they fall into thicker air, which raises drag again. That feedback loop can turn a bad day into rapid decay. This is most dangerous right after launch, when satellites are placed in lower orbits for checkout. In that phase, the margin to climb is limited. Early February 2022 showed the risk in public. A batch of 49 Starlink satellites launched into a low orbit. A geomagnetic storm increased atmospheric density and drag, and many of the satellites could not climb out. SpaceX commanded a low-drag configuration, but it wasn't enough, and about 40 were expected to be lost to re-entry. That's a design and ops lesson. Storms don't just glitch electronics, they can change the orbital math. The 1-hour warning and the safe mode decision. Picture a normal ops shift. Telemetry looks boring. Everything is stable. Then the upstream data spikes and the forecast turns from watch to act. The next move isn't a brainstorm. It's a choice between pre-built postures. Hold steady, reduce risk, protect the bus. The human temptation is always one more. Storms punish that instinct, so good fault protection removes debate. 20 minutes of silence on the way to Mars. Far from Earth, you send a protection sequence and then you wait. If autonomy is strong, the probe downshifts cleanly, protects power, holds a stable attitude, and keeps communications predictable. If autonomy is thin, the gap becomes a trap. A small upset can start a chain, and by the time the ground sees it, the spacecraft may already be out of margin. That is why deep space design keeps circling back to the same rule: self-preservation first, science second. And when the storm passes, the real work begins. Recovery, what coming back online really looks like. Safe mode saves the spacecraft. Recovery is the bill you pay. First comes the basics: stable attitude, stable power, stable thermal, and a clean communications link. Often that means low data rates and conservative pointing. Then the team answers the uncomfortable question: what exactly tripped? Only after that do you start waking things up, staged and careful. Power comes up in steps. Thermals get checked at each step. Attitude sensors get validated before you trust precision pointing again. Instruments return one by one, each proving it isn't pulling the wrong current or producing nonsense. Sometimes recovery is a few ground passes. Sometimes it's days, especially for deep space missions where every command cycle is slow and you don't rush a restart. How spacecraft design changed, the clear difference. Across decades, the pattern is consistent. Early satellites survived on simplicity and narrow limits. Modern spacecraft keep that simplicity as a fallback, but add redundancy and fault logic that can intervene fast. Charging went from weird edge case to a driver of materials, coatings, grounding, and operated from ground-driven recovery to onboard autonomy, cross-checking, and error-correcting memory. Shielding changed too. Less everywhere a little, more protect the brain with vaults and spot shields. And constellations learned, sometimes the hard way, that storms can change the atmosphere enough to change the orbit. The real secret, it's a systems problem. There isn't one hero component that beats a solar storm. Survival is layered. Hardware that tolerates hits, software that doesn't panic, fault rules that choose stability over performance, and operators disciplined enough to sacrifice data instead of gambling the spacecraft. So answer this like you're the one on the hook. If you're responsible for $1 billion spacecraft, do you safe early every time? Or do you ride closer to the edge to keep the mission producing? If you want more behind-the-scenes reality like this, hit like and subscribe.